Hello once again to another time value of money video. I would now like to derive for you the equation for the application formula for the present value of a growing perpetuity. Now, a growing perpetuity is a cash flow stream that never ends, has an infinite number of cash flows, and each cash flow is bigger than the cash flow that preceded it by a constant proportion or percentage. So, in this example, the growth rate of the cash flows is shown as lowercase g. You see it right there. Okay? So a growing perpetuity cash flow might have at say, date 1 a cash flow of C, at date 2 a cash flow of C times 1 plus G, a cash flow at date 3 of C times 1 plus G squared, and so on. Okay? Again, the numerator terms here are just the cash flows. Okay, so that's the cash flow stream. Now here I want to derive the application formula for the present value of a growing perpetuity. So we start off with equation 1. Present value of a growing perpetuity is equal to the cash flow at date 1 divided by 1 plus the opportunity rate of return R. So this cash flow here is presumed to occur at date 1, and when I divide it by 1 plus R, that's the same as multiplying C by 1 over 1 plus R, so I'm moving this C back one period in time. The next cash flow in this growing perpetuity would be C times, this is a parentheses here, it's not a double C, that's a parentheses. Again, C times 1 plus G now, excuse me, because this cash flow is larger than this one, and the G is the amount by which it's larger. So you can see we have C plus G times C. So, you know, G is the growth rate of C, of the cash flow. And this is divided by 1 plus R squared. That moves this value back to date 0. And the next cash flow would be C times 1 plus G squared. That would be the date 3 cash flow. And then to move that date 3 cash flow back to date 0, we divide it by 1 plus R cubed. Again, it's the same as multiplying C times 1 plus G squared by 1 over 1 plus R cubed. Okay? And then a plus and then dot, 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 because this continues on forever. Okay? So remember, we're trying to find a formula, an application formula, to determine the present value of a growing perpetuity. Now, this is our third type of multiple cash flow stream. The first one we saw was an annuity. The second one was a perpetuity. And this one, our third one, is a growing perpetuity. So for example, the cash flow at date 1 might be 100. The cash flow at date 2 might be 110. The cash flow at date 3 might be 121, thereby showing a growth rate of 10%, decimal equivalent of 0.1. Okay? So now we take equation 1, okay, and we multiply both sides by the same factor. And the factor is 1 plus G over 1 plus R. Okay? Remember, G is the growth rate of the cash flows. R is the appropriate opportunity rate of return. So taking equation 1 and multiplying both sides by 1 plus g over 1 plus r. So on the left-hand side, we have present value of growing perpetuity times 1 plus g over 1 plus r. Okay? Now I take this term and I multiply it by 1 plus g over 1 plus r, and I get this. I take this term and I multiply it by 1 plus g over 1 plus r, and c times 1 plus g over 1 plus r squared, when multiplied by 1 plus g over 1 plus r, becomes c times 1 plus g squared divided by 1 plus r cubed. Plus, and it continues forever. Okay? Now, this equals this, and this equals this. Therefore, logic tells us that the difference in the left-hand sides of the two equations, 1 and 2, must equal the difference in the right-hand sides of these two equations. Okay? Now, just keep in mind that with this multiple cash flow stream, as is always the case, we're building our interest factors and our application formulas so that we always value the cash flow stream in present value terms as of one period prior to the first cash flow. So we did that with annuities and with perpetuities, and now with a growing perpetuity. We're going to find the value one period prior to the first cash flow. Okay? In this case, I'm presuming the first cash flow is at date 1. One period prior to that would be 0. But an important point to realize is this. If the very first cash flow occurs at date 15, and then this numerator is date 16, and this numerator is date 17. So starting with date 15, then using this formula will give us the value as of date 14. And if we ever wanted to bring that value back to date 0, we would then have to take our calculated value here, which we're getting to, and multiply it by a present value interest factor, moving it back 14 periods. That will be 1 over 1 plus r raised to the 14th power. Okay. So now we take the left-hand side of equation 1 and subtract from it the left-hand side of equation 2. So I have PVGP minus this, 1 plus g over 1 plus r times PVGP. Now the right-hand side is easier, okay? Because we have some canceling going. Now we don't get any canceling with this term, okay, because this term doesn't appear down here. But here we have c times 1 plus g over 1 plus r squared. And here we have c times 1 plus g over 1 plus r squared. So this cancels with this, okay? And then our next term here is c times 1 plus g squared over 1 plus r cubed. And we see that's our term here, c times 1 plus g squared over 1 plus r cubed. So these cancel. Since both of these right-hand sides of the equation go on forever, okay, infinitely, everything that's up here is also down here and will cancel. So all that we are left with on the right-hand side is this term, c over 1 plus r. Okay? So now I'm going to multiply, we have 3 terms, 1, 2, and 3. I'm going to multiply each term by 1 plus r. So here I have 1 plus r times present value of a growing perpetuity. And then this becomes, when I multiply it by 1 plus r, it becomes 1 plus g times present value of growing perpetuity. And that equals c. Okay? Now I'm going to factor out a PVGP. And of course I have 1 plus r minus 1 minus g. This is minus g because I'm distributing this minus sign over 1 plus g. Okay? And of course the 1's cancel, and by the way that's equal to c, so the 1's cancel. So I'm left with present value of growing perpetuity times r minus g equals c, and then we're done. Next step, present value of growing perpetuity equals c divided by r minus g. Now this is true for r greater than g. The opportunity rate of return has to exceed g. If this is not true, if g exceeds r, for example, then this term will approach infinity. The reason it would approach infinity then is because if G is greater than R, you can see up here, then 1 plus G, well, let's look at this term first. Here I have C over 1 plus R. And now I'm going to multiply this by 1 plus G over 1 plus R to get this. But if G is bigger than R, then 1 plus G over 1 plus R is going to be bigger than 1. And so the idea is, therefore, this term will be larger than this term. And because I multiply, in order to get this term, I multiply this by 1 plus G over 1 plus R. Because 1 plus G over 1 plus R is greater than 1, this term will be larger than this term, and that never ends. So the sum will be infinite. So the present value of a growing perpetuity is equal to the cash flow at date 1 divided by R, the opportunity rate of return, minus G, the growth rate of the cash flows, for R greater than G. A growing perpetuity is an infinite cash flow stream. Again, think of maybe the first cash flow at date 1 being 100, and then at date 2, 110, at date 3, 121, at date 4, 133.1, and so on. That would be an example of a growing perpetuity if it never stops. Now, we're about to look at another proof. This is a proof for determining the present value of a growing annuity. Now, a growing annuity is like an annuity in that the interval between the cash flows is constant, and in that the number of cash flows is finite. But a growing annuity differs from a regular annuity in that the sizes of the cash flows differ. In fact, we'll have the same relationship between successive cash flows with growing annuities as we did in a growing perpetuity. That is, each cash flow is bigger than its predecessor by a constant. For example, here we have, in other words, and again, we're building this present value of a growing annuity application formula to give us the value of the growing annuity one period prior to the first cash flow. Always keep that in mind. That's true for present value of annuities, present value of perpetuities, present value of growing perpetuities, and present value of growing annuities. It's true for all of those. So here we have the present value of growing annuity equals the date 1 cash flow discounted back 1 period, therefore divided by 1 plus R, plus the cash flow at day 2 divided by 1 plus R squared, plus ... and then the last cash flow in this growing annuity, the cash flow at date N, divided by 1 plus R to the nth power. Now down here, just for convenience, I'm restating C1 as C0, the cash flow at date 0 times 1 plus G. And then I can call the cash flow at date 2 C0 times 1 plus G squared. And of course, the cash flow at date N would then be the cash flow at date 0, C sub 0, times 1 plus G to the nth. And then I divide them by 1 plus R squared, out here 1 plus R to the nth, of course, as you see. So I can now summarize this first equation, the definitional equation of a present value of a growing annuity, PVGA, equals the cash flow at date 0, because I factor that out, times another thing I can factor out of each and every one of these terms is 1 plus G over 1 plus R. So I have C sub 0 times 1 plus G over 1 plus R, and then that's this entire term here, so this is a 1. And then here, when I factor this out, I'm left with 1 plus G over 1 plus R. The next term, when I factored this out, I'd be left with 1 plus G squared over 1 plus R squared. Excuse me. And so on up until this last term, when I'm left with 1 plus G over 1 plus R to the n minus 1 power. Okay? So this is our equation 1 now. And now what I'm going to do is I'm going to create equation 2 by multiplying both sides of the equation, left side and right side, by 1 plus g over 1 plus r. So over here I get 1 plus g over 1 plus r times present value of growing annuity. And then of course over here, this doesn't change, but the 1 becomes 1 plus g over 1 plus r, and this becomes 1 plus g over 1 plus r squared, and so on, and the last term becomes 1 plus g over 1 plus r to the n power. Okay? Now, as has always been the case in these proofs, we start with a definitional equation, then we multiply both sides of the equation by a factor, and now we just use logic. If this equals this and this equals this, then the difference in the left-hand sides logically must equal the difference in the right-hand sides. So here I calculate the difference in the left-hand sides. It's 1 minus 2, so PVGA minus 1 plus g over 1 plus r times PVGA. And then over here, it's this minus this. Well, the CO times 1 plus g over 1 plus r factors out, of course. And then we have a lot of canceling going on. This term cancels with this term. You'd agree this term would cancel with the next term here. You'd also agree that this term would cancel with the term that precedes this term. And so all we would be left with would be this 1, and then down here, this 1 plus g over 1 plus r to the nth power. Okay? And since it's equation 1 minus 2, remember this is equation 1 here, just modified. So equation 1, equation 2. And therefore, in the square brackets, all we have is the 1 minus the 1 plus g over 1 plus r to the nth. So now, I'm going to multiply every term. I have 1, 2, I guess 3 terms. I'm going to multiply all my terms by 1 plus r. So I get 1 plus r times PVGA. This becomes 1 plus g times PVGA. And here I get C0 times 1 plus g. And then in the square brackets it stays the same. I don't multiply this by 1 plus r. That would be double counting because this is all one term. And now I factor out a PVGA and I get 1 plus r minus 1 minus g. Again, it's a minus g because I'm distributing this minus over the plus g. Okay? And here, on the right-hand side, nothing changes in this step. And here, the 1 minus 1 becomes 0. So next step I have present value of growing annuity times r minus g equals the same thing over here, doesn't change. And then in the final step, when we're done, the application formula is being proved. The present value of a growing annuity equals, now this numerator right here can be thought of as the cash flow at date 1. Or, as it shows here, the cash flow at date 0 times 1 plus g. But I will leave it like this, divided by r minus g times 1 minus 1 plus g divided by 1 plus r to the nth power. So here we've proved that the application formula for a present value of a growing annuity is equal to the cash flow at date 1 divided by r minus g times 1 minus 1 plus g over 1 plus r to the nth power. And that's all for this video. Thanks for watching.